Okay, let's get started. Okay, so the next talk will be given by Adam Kalai from OpenAI. Adam's been working in the field of machine learning, learning theory for many years. He was a founding member of Microsoft Research New England before joining OpenAI. Says he's been working in his bio. He said he's quite old and has worked in multiple fields, including algorithm, fairness, machine learning, theory, game theory, and crowdsourcing. Goes on for a while. He has many awards, including the Major Look Prize, Best Paper Awards, NSF Career Award, and the Alfred P. Sloan Fellowship. And so we're looking forward to your talk.
Thank you. All right, great. It's great to be back at Simons. I love coming here. And I'm going to talk about work I'm doing. Is the microphone on? Can you hear it? Or not really? No? They say they can't hear. Are they? Okay, can you guys hear it now? Is it better? Okay, thank you. Okay, now I gotta be careful, right? I'm working at OpenAI now on hallucinations of practice, but today I'm gonna talk about the theory. They're a little related. And this is joint work with Santosh Vempala, and it's work I did while I was still at Microsoft Research. And if I have time, I'll talk more about some other issues in generalization as well, but hallucinations are actually a generalization issue, I will argue. So I think it fits pretty well. Okay, so, and I just want to thank Shafi for running Simons. I love, it's probably my, oh, never mind. Thank you, other people who are running it now. Okay, so let's start with an example of a hallucination. So you can ask the language model to write an obituary for Adam, Tom, and Kalai, and it'll happily, ChatGPT will happily write one, and it'll say, Adam Kalai, a luminary in the field of computer science at Arthur passed away on April 1st, 2024. That's not my age. But anyway, it would be great, by the way, to die on April 1st. If you die on April Fool's Day, can you imagine my wife trying to call my friends and telling them that I died? No, nobody would believe her. And they'd all be like, either I'm pranking her or she's pranking them. Anyway, so I'm going to try to do that, to die on April 1st. All right, so, but you know, it goes on and it talks about he's survived by his beloved wife, Rachel, which you guys know is not true, and his two children, Samuel and Emily. No, it could be. I don't think so. Children, I have two more kids. All right, anyway, so it's pretty funny, but there are some serious examples of hallucination where, you know, lawyers are submitting cases, or even worse in medical domains where people get bad advice. So we really, really don't want these language models to hallucinate. It can be very harmful, potentially deadly. So we want to work on this, right? And there's just no end to these situations. So what is a hallucination? It's a plausible, it's already a word in the dictionary, actually, the third entry. A plausible but false or misleading response generated by an AI system. So it has to be plausible, right? But false. Okay, and let's go through some examples just to make clear what it means. So like the first example is, you know, you've heard this fact that humans only use 10% of their brain. So I'm talking about language models in the old school sense of a probability distribution where, you know, you give it a prompt, a prefix, and it completes the rest of the sentence. That's what's happening behind the scenes in a ChatGPT or any other language model. Okay, so you give it a prompt and it's trying to predict what comes next. Now, I don't think of this really as a hallucination. I mean, it's in the training data. We know where it came from. If you want to get rid of that stuff, I mean, maybe you just take it out of the training data or whatever, but it's not really like this mysterious, you know, where did that come from? Or there's other types of hallucinations, like John Doe was born in 1979 and died in 2025. Well, that's really more like a miscalculation. And in this talk, I'll explain kind of how you might separate these different types of mistakes, hallucinations, or why we don't expect actually language models to necessarily have these kind of errors. But we do expect language models to have hallucinations unless we fix it. So I don't think hallucinations are inevitable. I think we can fix them. But I'm going to explain why they're happening in the first place. So this is definitely a hallucination if it says Adam Kalai. If you say the word fact, and then after it just generates Adam Kalai died on April Fool's morning in the hospital after suffering. So, you know, that's the kind of thing that humans don't do so often. And, you know, but we do make the other kinds of mistakes, and it's kind of curious about why that happens. And feel free to interrupt me during the talk. Okay, so I'm going to talk about language models. So again, what do we mean by a language model and pre-training? So a language model is just a probability distribution over binary strings of documents, okay? That's the simplest definition. And we assume we have some training set, of documents. And there's some distribution, some true distribution, D, over documents. And we're going to try to approximate this distribution. So, a natural criteria is you try to maximize the likelihood of the training documents, or equivalently maximize the sum of the log likelihood of the training documents. What distribution optimizes this? Yeah, uniform over the training data, the stochastic parrot distribution, which just repeats a random training document. So that's not actually what we want to do, right? That would be a not very useful language model. You could generate it, but it would be just memorizing the training distribution. We really want generalization. We really want to maximize the expected log likelihood over future examples drawn from this same distribution. Okay, so yes, thank you. Should be a sum. And this can be used to complete any prompt. So you give it a prefix of some text, of some document, and then if you have a distribution, you can look for the probability of each subsequent word and generate from that distribution. So these language models are randomized. They don't generate the same thing every time. They give you different answers. They're probability distribution. And some people think that hallucination happens because it's generating one word at a time, but I don't think so. I speak one word at a time, and I don't hallucinate that much, unless I want to. So just to make that point, obviously the probability of a document can be computed by probability of one word at a time. So you could say the first word is the with probability 40%. Here's a distribution over sentences which are all true. It's not going to hallucinate, and it's one word at a time, and it's the. Then sun happens after the with probability 50% and rises with probability another 50%. And you get the probability the sun rises 10%. And so maximizing next word probabilities is like maximizing document probabilities. Okay. And then maximizing, equivalently, maximizing the expected log probability of documents is the same as maximizing the expected log probability of each word, given the previous words. By the way, I've given this talk a bunch of times, but today I'm going to try to throw in a new result. So we'll see if it works. If you've seen this talk, then there's something new. All right. And side note, we're ignoring computation here. Okay. So this is only for information theoretic result, but it's a lower bound, so it's stronger. So maybe maximizing next words is actually, computing one word at a time could actually make things harder if you can consider computation, but if you ignore computation, it's completely equivalent. So there's many reasons why language models may hallucinate. One is that you may have bad training data. Okay, true. You may have a bunch of false facts or false non-facts in the training data. You could have like a tricky prefix, a prompt. Like I could give it a prompt. There's just no way to complete it correctly, obviously. But what I want to say is actually hallucinations arise naturally whenever the fact distribution is not easy to learn. Okay. And so the assumptions I'm going to make are that every training document contains one fact. Okay. These are strong assumptions that everything is either a fact or a hallucination. There's no gray area in the middle. What? No myth. No myth. So the first one is that there's no myth. There's no training. There's no everything in the training distribution is fact. No myths. Second one is that everything is either a fact or not. The third is that the documents are IAD. The fourth is that every document starts with the word prompt fact, and all the prompts are the word fact. Now this sounds like, oh wow, these are really strong assumptions, but actually this is a good thing because we're doing a lower bound, right? So I'm saying even in this ideal world, right? Even if I try to make life as easy as possible, there's one fact per document. There's no gray area. Things are IID. Do you think we're going to have to hallucinate more in the case where you have training data with mistakes in it? Yeah, when the distribution is changing over time, and and when documents have many facts and some of them are kind of gray area and stuff. So yeah, so the real world is even harder. But I'm trying to say, even in this ideal world, we're going to have to hallucinate. So there's a statistical basis for why we're hallucinating.
Facts are allowed to appear like 0, 1, or more times, like any number of times?
Yeah, it's just, I just drawn from a distribution. There's a distribution of our facts. We're drawing samples, and yeah. Yeah.
Why you didn't include hallucination in the training?
Say it again.
The training dictums are only facts, right?
Yeah.
Why don't you train also the model over hallucinations?
Why don't we train on hallucinations? Well, I'm saying even, like, one reason that people say models hallucinate is because the main reason, if you look at applied papers, why do they think language models hallucinate? They think it's because they haven't done a good job cleaning up their training data, because there's a lot of hallucinations. I'm saying actually that's not even the only reason. Like, even if they did a perfect job cleaning their training data and you maximize the log likelihood, you try to optimize for cross entropy, they call it, which is what they do in the pre-training stage, then you'd still get hallucinations.
Is that the claim that people make? I mean, I've seen a lot of discussion of hallucination.
Yeah, there's
I haven't seen people give such a
a very common, I think a very common explanation for why people think that language models hallucinate is, there's certainly a bunch of papers on that, but do you have other explanations you've seen?
Sure, but let's.
I mean, some people say language model must hallucinate because they assign non-zero probability to every word, so therefore they must be able to generate anything. But that doesn't give you any bounds. It just tells you that that you have to some minuscule probability of.
Well, a common notion is that they're resolving their epistemic uncertainty by, like, you ask it, you say you're a doctor, I have the following symptoms. It's like, well, a doctor would know, a doctor would speak confidently. It doesn't happen to have the information.
Right. Yeah. So the prompt. Right.
You definitely don't have cancer. It doesn't know which, so it generates one of those 50-50.
Right. So the good. So first of all, I'm going to avoid the prompt issue because we're having that, and it'll be interesting to see how that compares to what you're saying. It'll be interesting.
How do you define fact?
Oh, so just abstractly, there's a set of facts. Every document contains some fact, and just a general case. So even in that simple case where every document contains one fact, there's only one way to write every fact. Life is so simple. We're still going to have to hallucinate. So given the real world where there's many ways to write a fact and there's many things, we'll still have to hallucinate.
So, so John Schulman has a talk, I think, at Berkeley a couple of years ago, where he points out that if the model is ever trained on a fact that it sees only once, then it has to run. Okay. So I mean, that's
with what probability? Yeah, because language models typically are full support. They'll output every word with some non-zero probability. So they will hallucinate almost by definition in that sense. But in this talk, I'm going to talk about the rate of hallucination on different problems, and that's kind of what we're getting into. But yeah, so there's a bunch of reasons why explanations for why language models hallucinate. Maybe I'm not doing justice to all of them. I mean, maybe people have different types of language models, but typically, like, it's just much easier to do gradient descent. Like, if you have zero probability on a word, then it's going to be hard to get out of that. Anyway, that's not a claim I'm making. It's not necessary for my results, so let me just drop that. I don't have an opinion on that. It doesn't matter. If it were true, then obviously the language model would have to hallucinate with some non-zero probability, but it wouldn't mean much anyway, but maybe not. Okay, so we're talking about these sort of factoids. Let's imagine sort of these arbitrary facts. They could be true, could be false. And I'm going to start with a motivating example of these obituaries. So let's say that, let's make it simpler and simpler and see why the language models must hallucinate. So what if the distribution is really simple? I'm going to ask you guys to be a language model today. Okay, so here's your job. It's tough to be a language model. I mean, here's your training data, and you need to come up with a distribution that models this training data. Okay, you've got these facts. As you can see, there's a celebrity here, Alan Turing, who died on a certain date, and then every other one is just some nobody like me who died on some date, and it just appears once in the training data. Okay. All right, so does anyone have a candidate distribution that they want to propose to fit this data?
Alan Turing died on that date. Random people died on random dates.
With what probabilities?
You know, uniform over the period from like
Right. No, but which probability Alan Turing and which probability a random person?
Well, are we just generating a random?
Yeah, you have to come up with the.
Yeah, so 50% of the time we say that Alan Turing died.
Uh-huh.
And on the correct date,
Yeah.
50% of the time.
A random person. Good. So that's exactly what I was thinking. Does anyone have another distribution to propose, by the way? But I like Russell, so that half the time Alan Turing died in this date, and half the time a random name died at a random date. And this is not a great distribution at all. It hallucinates almost 50% of the time. But it's calibrated. But okay, does anyone have a different distribution to propose?
The uniform distribution.
Uniform over the training data. Good. So that won't hallucinate. It won't be calibrated, or it won't generalize. Calibration is a type of generalization where you're essentially saying, look, it says that 20% of the time Max Clemmer Fennel died on that date. But if you look at future examples drawn from the training distribution, that's not 20%, right? That's not going to happen even once again, probably. So calibration means generally that that among facts that you predict with a certain probability, let's say 20%, all the facts that you say that you think will occur with 20% probability, on average, they should appear 20% of the time. It's a very elegant notion, and it's very simple in principle to achieve, because you could actually take the uniform distribution over any set, and that's calibrated, because you say, oh, I think 50-50, or not 50-50, 1 over n for everything, and among the things that you predict with probability 1 over the size of the space, they do occur with that probability. So it's a great notion. It's kind of a lowest bar, and language models are often calibrated in some. There's different metrics for calibration, but they do measure it, and they do find that the pre-training stage, when you maximize the log likelihood, you do end up with a calibrated language model often.
Sorry, maybe not understanding.
Yeah.
So for me, that seems like an incomplete answer, because still, what is the probability of each possible random name that you could put?
Oh, yeah, we'd have to make this really formal. We'd have to like formalize the probability of every name in the dictionary. Is that what you mean?
Yeah, well, what is even the space of possible names? So
Yes. Yeah, but this is a toy example. I'm trying to show that language models would have to hallucinate. So let's assume we have a fixed bag of first names and last names and some fixed distribution over names and death dates, and everything is simple and perfect. Even then, I want to argue we'll have to hallucinate. So.
And also, how is this calibrated? Because you said, okay, if you predict Max, Kenneth, whatever, 10% of the time, let's say, you don't know if that's actually going to happen.
Let's assume that there is an IID distribution. We can split our data into train and test, and then we can evaluate and see, okay, you said 10% of the time Max Kenneth Fennel died. You said that that's going to happen, or this set of things will happen with 10%. Then we look at the test set, and we say, oh, our predictions are not very accurate. You're expecting, on this million-sized test set of 1 million examples, you expect 10% of them to be Max Kenneth Fennel died, so it should appear 100,000 times, and it appears 0 times. That's a sign that your probability distribution is bad. It's not generalizing. It's not calibrated. Does that make sense?
Yeah, but the same thing could happen with the Turing phrase. Now, maybe.
No, but I'm assuming there's an IID distribution, that documents are drawn. So there's some process by which people create documents. Again, this is like an idealized assumption, and I'm saying even in this case, we'd hallucinate. So in an ideal world where people are just writing documents and nothing changes in the world, and there's a distribution over the stuff that you output, we want to model that distribution. It's a distribution fitting question. I'm not saying this is a realistic model of how people, the real world. The real world is even more complicated. But even in this pure, simple world where people write documents, they write poems, or they write whatever they want, you still need to hallucinate. Does that make sense?
No, I mean, I just didn't get your definition of calibrated. Maybe it's too.
Oh, I didn't define calibrated very carefully. But what it means is that among, so your language model predicts probabilities on all the facts. So for every probability that you might predict P, if you look at all the facts that you predict with probability P, there's some true distribution out there. And on average, the probability of facts that you predict p width should be p. So the easier way to think about it is there's some set, of facts, and there's some density on this set, D, that's the true. There's some true D. And then, I'm glad you're asking this because I think it's not clear. And then every predictor, every D hat, you can think of the level sets, where you say, okay, here's D hat is, D hat is going to be really small, 1 in a million here, whatever. And among these, so, you should be on average 1 in a million. So the best way to think about a calibrated language model, and this is a formal definition, is you take, it's a partition of the space X. These are the factoids, which could be true or not. And you partition it, and then there's a true distribution D, and in each region you have to be uniform. You have to have the same, the average probability. Your probability must be the average of D. So these are the regions where you're constant, and you must just be an average of the true distribution in each of those regions.
So one thing that might be counterintuitive, if I'm understanding,
yes, thank you,
is that if you just take the uniform distribution of
right.
all factoids,
yes,
it's always calibrated.
It's calibrated because it's just basically you have a trivial partition in one set, and you just assign the average probability, which is 1 over the number of facts, to everything. It's a very minimal, it's not a very strong notion. You can be calibrated and be a terrible language model, but you might as well be calibrated is the point. Like it's hard to evaluate language models for accuracy, or you look at entropy, but you never know when you've actually reached the ideal entropy. It's hard to know, but calibration, you can check.
So if the distribution you're going to sample from is reported in a large set, you can just say, I don't know. Not abstain from it.
I don't know.
So you can basically throw, so in real world, if you really don't know
oh, yeah.
when a random person dies, so you can basically,
yeah, I mean, you could, and that's not a bad proposal. Rather than generating Russell's distribution, you could just say, I don't know, all the time, and you would be factually correct, but you wouldn't be very calibrated, or, because if the training data has no I don't knows in it, you are definitely going out of distribution and not calibrated by generating I don't know.
So I'm not saying how to target it,
I'm just saying it's not calibrated distribution. You're not doing well in the objective of being calibrated or maximizing generalization.
Although it has the same advantage of that calibration does, that you can make downstream decisions about what to do with the output of the model. And that's what we want calibration for. I don't know is correct with probability 0, and you know that. And so you can decide.
I'm not saying it's a bad thing. I'm just trying to understand why this mystery of language models hallucinating is happening. And I agree that maybe saying I don't know all the time is better than what we're doing in some cases.
Yeah, so assuming your calibration definition here is your model distribution is super close to the word distribution, right?
Not at all. Right, like Russell said, the uniform distribution over all facts is calibrated, and that may be very, very far overall, not facts and non-facts over all plausible statements is calibrated, because it's a partition of the space, and you just put, like the weather forecaster who says, if it rains half the time, the weather forecaster who says, I think it's going to rain half the time, they're calibrated. Seems like they're right. Maybe somebody else can give a much more accurate prediction. They say, on that day it's 90%, on that day it's 10%. But so calibration is just kind of a crude notion of accuracy that's easier to achieve.
So you said that you might as well be calibrated because it's easy. And I can see the benefits of being calibrated, but I also feel like we're going to talk about a downside that comes from being calibrated. Yeah. So why should we think that you might as well be calibrated?
Well, I'm not saying you should be calibrated, but calibration does follow from pretty much follow from maximizing log likelihood. So another thing you can show is that if you have a distribution and it's not calibrated, and you take your distribution, you say all the times where I predicted 1 in a million, I was better off predicting 1 in 2 million if it was miscalibrated. By doing that type of post-calibration, you actually reduce your log loss. You increase your log likelihood. So the way they're trained to maximize log likelihood naturally motivates the language models to be calibrated.
So how does this sort of mesh with the modern pre-train, post-train kind of paradigm? Like when you're post-training, you're doing reinforcement learning style objective.
Yeah,
right?
Exactly. I'll get to that. Yeah, good question. Thank you. But yeah, pre-training is generally to maximize the log likelihood. They call that pre-training. It's training, not pre-training. But anyway, okay. Great questions, thank you. So then we have the stochastic parrot model, which Daniel recommended of, the training data doesn't hallucinate, but it's not predictive, it's not generalizing, it's not even calibrated. You could also just do the distribution, which is 100% Alan Turing died on that date. But this example, which is trivial, just really points out the binds that the language model is in. Or you can say, I don't know. But you either match the training distribution, you either try to match the training distribution and generalize, but then you're hallucinating half the time, or you don't match the training distribution, but then what are you doing? It's hard to define it mathematically. Okay, so let's get into the theorems. So, we have this set of plausible statements P, which are divided into facts, F, and everything else, which is the hallucinations. And then there's, the training data, which is very sparse, right? So the training data, the green is the training data, the white are the facts, and then the hallucinations are everything else, right? Like everyone else who could have died. There's so many plausible statements which are just not true. So the assumption generally is that the training data is much smaller than the number of facts. If there's training data was as big as the number of facts, you would have seen everything and then life would be good. But there's no way we're going to get that. There's so many facts. What you had for lunch yesterday, well, everyone has so many facts about them that are not in the training data. And then there's the hallucinations, which are the false things, which are way bigger than the facts. Okay. All right. So let's start with a warm-up case where you imagine that the facts are really just random statements. So like what's true is uniformly random. So there's some set of uniformly, let's say fixed size, uniformly random set of true statements, F, which is a subset of the plausible statements. And the data distribution is even uniform over these facts. And we just see a subset of them. So it's very sparse. Okay. So then we can say with very high probability, now we get into the rates, the probability that we generate a hallucination is at least 1 minus a term here, which is based on the miscalibration. So if the language model is perfectly calibrated, like I described here, then it would be, that's a 0. So it'd be 1 minus the number of training examples, n, which is huge, but it's not nearly as big as the number of facts, F. So this is a tiny fraction, minus 200 times the ratio of the facts to the hallucinations, which again is tiny. Okay, and so that's the case where everything is independent and random. Any questions?
Assume that 200 is just being cautious.
Yeah, probably you could improve the constants in all the things in this talk. Okay. Okay, then you could, in the Alan Turing example, we had it wasn't a uniform distribution. What if your distribution isn't uniform, but still it's symmetric? So the size of facts is still fixed, but there could be like you decide that half the facts are going to be the same, and then the other half of them will be different. But which fact is which is true is still random and symmetric. Okay, so it's kind of confusing. It can be symmetric but non-uniform. Okay, and then we get an interesting quantity here called the rare fact rate. So the fraction of facts, which is related to what Sanjeev said about John Schulman's talk. I guess he gave a talk. I didn't see that work. But where he talked about the fraction of things that appear. So this is the rate. So the fraction of things that appear just once in the training data gives you an indication of how much you expect to hallucinate. Okay. In the case where it's a symmetric distribution, you get that minus the miscalibration. And then you have a 1 minus delta probability. And then you get this fraction of facts to hallucinations and some other term. Again, n is the number of training examples. So this is a very small term in the end. Okay.
Can I assume it's very close to 1 because based on assumption we make?
Which is very close to 1?
RF and DH.
Oh, RF, the rare facts. Well, it depends. In my example with the celebrities, it was half, right? Like half of the training data was Alan Turing died on a certain date. There are facts that are repeated many times in the training data. And then there will be facts that aren't very rare. So I just feel like it's a parameter. But yeah, I think it depends on the domain. In some domains, it's pretty much you never see something twice. In other domains, you see a very small number of things and you see them often. And in some domains, it's a mix.
So once is an arbitrary choice.
What did you say?
Once is an arbitrary choice.
Oh. If you go fishing and you catch 100 fish, and there's, and there's a bunch of fish that you catch once, that kind of represents, like if you caught 100 fish and they were all different, you kind of feel like the next fish is going to be different too. If you caught 50 fish twice, you'd be like, I don't think I'm going to see that many new fish, every fish I've seen. So it's not. It's actually a great question. I wonder if that's the... So it's related to this Good-Turing estimator that Alan Turing has for what's called the missing mass. So this fishing question of when you go fishing and you have a bunch of fish and you try to catch them and you count how many fish appear once, that's a very good estimate for the probability that another fish coming from the same distribution will be new and unseen. And you can kind of get intuition for that because this is like each fish is like an experiment where if you held that fish out and you said, okay, what is the chance I would have predicted that fish had I not seen that? So that's a good estimate of the missing mass because it's like, oh yeah, that would have been a new, if you got 100 fish and then each one you think about, oh no, what if I'd gone 99 times? What's the chance that the next fish would have been new? Oh, and that's 100 experiments, not independent, but 100 samples of that experiment. So that's the beautiful missing mass estimate of Alan Turing. Good just wrote it up, but he gets his name there.
So it's the number of training samples, but the inequality on the previous page shows that with more training samples, the hallucination rate is higher because DH.
Well, this goes down, but then this is the probability of hallucination, right? And this goes down, but this goes up. Sorry, the rare facts also goes down. Sorry, so the rare facts goes down because the more training examples you have, the fewer rare. We're getting backwards. The more training examples you have, the fewer rare facts you have.
But can't we assume rare fraction RF stays constant?
I mean, eventually, if you got infinitely many samples, you would see every fact. But it is true in many domains that it stays roughly. It isn't like zip flaw or something like that. I don't know. So sometimes, so for a big chunk of the distribution, it might be true. Like in the example we have of the obituaries, it would be half for a really long time till you started seeing like order the number of people and then.
Thanks.
Yeah, good question. These are great questions. Thank you. Okay, so the new result that I want to mention is that it's not just for independent distributions and the good, rare facts, but what about like facts that are not independent, like even the multiplication example I had, where you make mistake, where you make miscalculations and stuff like that. So I think this is more intuitive actually, is if you can't learn it. So the real criteria is learnability. So it seems mysterious, these things hallucinate. Think about it this way. Suppose you couldn't learn what is true and what's not. You can't learn to distinguish on future examples, is this a true fact about who died on that date or not? So suppose you have, let's say for the simplicity, you're trying to distinguish the true distribution D from the uniform distribution over all hallucinations, okay? And you can't distinguish that. If you can't even distinguish that, so that would, in the obituary example, that'd be, I can't distinguish a sample from the true distribution over who died when from a random person on a random date. If you can't distinguish those, then you're gonna hallucinate. Or put a different way, if you're calibrated and you don't hallucinate much, you hallucinate only epsilon fraction of the time, then you're gonna be almost perfectly accurate at distinguishing the true distribution over documents from a uniform distribution over hallucinations. Okay. So if you want to decide whether you think you need to hallucinate or how often you probably need to hallucinate on a certain domain, you can say, okay, how often am I, how accurate do you think I could distinguish, something true from something false? So for multiplication, if your language model is smart enough to do reasoning and multiplication and all kinds of stuff, then you can generalize. You actually don't need to hallucinate, right? Like we don't need to hallucinate on arithmetic problems. There's no need, no information theoretic reason to do that. And so this says, well, yeah, because we could distinguish, we could train a model given, true multiplication facts from false multiplication. We could learn to distinguish those. Facts about who died when, we can't really learn to distinguish those perfectly. We'll have a huge error rate, so we should still have some hallucination probability, and this relates the two of them. I'm not saying this constant is perfect, by the way. Okay, does that make Sense? And so formally, we have got a classification problem where the true function is 1 if it's a fact and -1 if it's a hallucination. And there's some probability distribution, which, to turn into a binary classification, you want to do pack learning. You have to have the distribution, which is, let's say half the time it's a true fact according to the true distribution, and half the time, there should be a 2 here. Sorry, new slide. 1/2 times the size of hallucinations is uniform with hallucinations. Okay. And then our classifier, and here's the thing, our classifier is going to be really simple. Our classifier is just going to be, does your language model assign probability bigger than some threshold? Anytime your language model assigns probability to some fact bigger than the threshold, and the threshold here is, this parameter square root of epsilon over 2 times the number of facts. Once you if you assign high probability to some fact, we'll predict it's true. So it's not even like you don't even need to look at the training data. From the positive examples alone, you're able to build a classifier. But that makes sense. Essentially, that's the challenge of language models. You're given positive examples. You're not given any negative examples, and you're supposed to do a good job. Well, if you're doing a good job and you're calibrated and you're not hallucinating, then you're learning from one-sided examples. So you better be able to distinguish. Does that make sense? You've got this harder problem. Even though it seems mysterious that they're hallucinating, actually, when you think about their job, it's really hard. They were trying to do learning from positive examples alone. That's a really hard task. It's harder than learning from positive and negatives. But we have all kinds of intuitions about learning from positive and negative. Yeah, I couldn't learn to classify a real death date from a fake death date. Sure, that makes sense. But why they're hallucinating, that seems mysterious. But actually, it's a harder task to learn from positives alone. Does that make sense?
What kind of learning algorithm would need to calibrate it?
Good. So what I'm saying is the learning algorithm is the following algorithm. You take your language model, which is, let's say it's a calibrated language model and it hallucinates epsilon fraction of the time. You train it, GPT-4, okay? And if it didn't hallucinate, or in some domain it doesn't, right? Then you take it and you just threshold it. Any fact which it produces with high probability, you say that's a real truth. Anything which it produces with low probability, you say that's not true.
Was it an inference time?
That's the classifier. Yeah, so it's an algorithm that learns from positive examples alone. It trains the language model as is. So this reduction does talk about efficiency. If there's some task which is computationally intractable to learn, maybe statistically you could learn it, but you couldn't efficiently learn it, then you will also need to hallucinate. Does that make sense?
No, what I'm saying is that your fix is a filter on top.
Yeah, it's just trivial thresholding of the language model to determine to make a classifier. Okay.
That's right. Epsilon is the rate of hallucinations.
Yes.
When it generates randomly. Is that right?
Yes. When you sample from the language model and it generates something, you look at that and you say, "Oh, is that true, or is that a?" Yeah, perfect. Thank you. Thank you for that.
Yeah. I think someone before asked about training on hallucinations, and you said that basically some people think that hallucinations come from when you have hallucination training data, and so that could contaminate it. But now you're telling us that it's actually not including the negative examples makes it harder. Which one should I believe now?
I don't think they're in contradiction. I'm just saying, even if you don't have any negative examples, you'd still hallucinate. Like hallucination is a natural byproduct of training with this log loss, of minimizing log loss.
If I had the negative examples, then I might be able to get a lower classification error, and then therefore maybe hallucinate them.
Well, you might, but I'm saying if you can't distinguish, so if you can't classify, if you can't distinguish even with, let's say, positive and negative training examples, then you're definitely going to hallucinate.
Yeah. Do you have? I guess my question then is, do you have a corollary, like a kind of corollary?
Yes, which is down here. So if you can't delta distinguish, if you can't distinguish, true examples from uniform hallucinations with probability, with accuracy more than delta, with error less than delta, sorry, then you need to hallucinate at least, and then you just take the reverse of this, delta squared over 9 fraction of the time. So if you can't distinguish like a real death date from a fake one with 99% accuracy, if you can only get it with 40% accuracy, then we give you a bound on how often you need to hallucinate.
So what would be a computational version of this?
Yeah, so suppose that the challenge is factoring numbers or something, or even harder, determining determining whether a three-step formula is satisfiable or something, right? And we cannot distinguish, three satisfiable from unsatisfied. Suppose you give me a distribution where we couldn't distinguish satisfiable from, or parity with noise is actually better, right? Like the distribution is on parity with noise problems, and our job is to distinguish, is it a random parity with noise problem from a or from an actual one where there's a true function which is 90% accurate. We can't distinguish those computationally. Information theoretically we could distinguish them beautifully. So we can't distinguish them. So therefore we would hallucinate. If we were trained on true parity with noise problems, every problem in our data set was a parity with noise problem. There was a secret that we didn't know, and it was given, it was hidden behind the scenes. We can't distinguish those from real ones. So when we generate, we're going to generate stuff that just looks like random bits. And we can't.
But the hallucination is not computational. The hallucination is defined as an hallucination.
Yeah, because they're not parity with noise problems. Because you want one where it's easy to detect.
I was wondering if you can put computational considerations on both sides of the counterpositive. So, answer.
Okay.
Even if this computation cannot distinguish, then it means that's good enough for getting your.
Yeah.
This is a quibble, but shouldn't the footnote be 1 minus delta distinguished?
Yeah, sorry. Yeah, it depends on what you mean by delta distinguish. Yeah, thank you. Thank you.
That's a lot
Yeah,
stronger.
yeah, you can't. Good, thank you.
Sorry, to make sure I'm following. So you're saying that we can put a filter on top of the probability and the threshold of the probability ones? Counter the point we started with, where we want to model that generalized.
Does it say it again? Does it go?
Earlier, I think you said that we want to model that generalized.
I don't know if we want to model that generalizes because it's going to hallucinate. but this is a way to. But this will, if you don't hallucinate, this will be if you're in a domain where you're not hallucinating, and there are domains where you don't hallucinate. Take a language model. I challenge you. Try to get it to get a country capital wrong or a non-existing. Give me a country that has 3 Z's in it. It won't do it. Like it knows the countries like the back of its own hand. And why is that? Because there's not many of them. It's like the distinguishing a real country from a non-country. There's no rare facts. You see the countries many times. It's an easy learning problem for a real country from a made-up country.
This is really interesting, but I'm also trying to understand broadly how we view. I think this came up in a few other talks as well of like language model generation would include writing fiction, right? So would you think fiction as now?
Not usually. Fiction, hallucinations in fiction are okay. They're not usually considered hallucinations because you want the language model to be creative.
New fiction.
Yeah, so that's okay. That's not the problematic domain for hallucinations, I would say. It's more factual domains where we're after something.
But the line is kind of thin now because, for example, in your initial example, when you said write an obituary for yourself and you have not died, so the obituary is going to be fictional because.
Yes. It's a good point. So that example is actually tricky because why did somebody ask for an obituary for Adam Kalai? Maybe I did die. That would be a good use of the language model, right? Suppose I died right now, which would be hilarious. Then I would hope that somebody here would ask for an obituary for ChatGPT. Please do, and it would be very useful because it would. Hopefully it would, but it wouldn't. Hopefully it wouldn't have made up my wife's name and the children got those wrong, which is not good. But unless you mean it as kind of a joke, so it's not clear sometimes. So it's not even clear the intent of the user when they're asking for something. Are they asking for a fictional obituary or are they asking for facts? So it's a bit. But what we all know is that it's super frustrating when you ask it to write the related work section of your paper, which would be the killer application of language models for all academics, and it makes up a bunch of references. That's a hallucination. And you didn't really want this fiction section of your paper. You wanted nonfiction.
Really, you just care about getting all the correct references. If it includes some fictional references.
Sure, yeah, definitely. Okay, I never thought about that.
But what is the insight, for example, of this kind of, maybe I'm a bit lost with the result, but what is your insight from this? on why, for example, the legal example, where you said, okay, right.
Good. So let me get there. So I will jump. Let me just pass through this, and then I'll get there. So first of all, I just wanted to mention they show empirically that pre-training leads to calibration. So they do these experiments where they show that. And as I said, if it's not calibrated, then you can make it. You can reduce your log loss further by calibrating it. Okay. So the conclusion. One conclusion, if you're in the sort of simple example, the hallucination rate after pre-training is at least the rare fact rate. How many facts appear just once? And let's think about what fraction of facts would appear just once in training data. So as I said, for country capitals, I would claim they don't appear once. They all appear many times, so we don't expect it to hallucinate. For books and articles, do you expect them to appear, what fraction of book and article titles do you expect to appear just once? The title and author, the citation.
The percentage of what? Percentage of articles that only get cited once might be high, but the percentage of citations that only appear once is going to be small.
The second one is what I'm after, but also, even I claim every article appears many times in the web. Like I try to put an article, I put it on my web page, I put it everywhere I can think of. And if it's published, archive, some archive clone copies it, and I try to add it's on my CV. So like people, the whole point of publishing a paper is to advertise it, whether or not it's cited. So in principle, we shouldn't be hallucinating on these. So it's kind of an interesting takeaway, is I don't expect, and like, I think it's just a stupid limitation of the language models and the way they're trained. Like any reasonable statistical algorithm would look up articles when it came time to, I would consult the database, right, if it wasn't sure. So I don't think we'll be hallucinating on these forever. Even maximizing the log likelihood doesn't require you to hallucinate on these kinds of facts, but we do. So that's kind of an interesting opportunity, shows you that we can improve in that way.
You just have a lower bound here. I mean, there could be.
Yeah, this is a lower bound, right? So that doesn't contradict it. It just said that we need to hallucinate at least 0. But right.
But we also dedupe the training.
Say again?
Dedupe the training data. So
That's a great question. Should you deduplicate, or how does deduplication interact with hallucination? What's your intuition? If you deduplicate the training data,
in this case, it has to have a
you'll hallucinate more, because if you're doing a good statistical job, you'll be like, oh, everything appears once, so I should make up new stuff. On the other hand, so maybe to address hallucinations, we shouldn't deduplicate the training. Maybe we should duplicate it. We should make many, many passes over it. What'd you say?
That'll fix everything.
Right. Well, that has a problem of regurgitation. Then we start memorizing stuff and we don't generalize. So that's a trade-off. With death dates, I do think we'll have it's a heavy tail distribution. We'll hallucinate a lot. And some people think, oh, let's add more facts to the training data. Like if we're hallucinating, let's just pump in more facts, more death dates. That'll actually just make you hallucinate, as well. I mean, it doesn't help. Okay, so, and we talked about this. So duplicating training data, or deduplicating, will increase hallucination or reduce training hallucination. Okay, so now back to your question over there about the post-training. So now we don't want to hallucinate, okay? We want to say, I don't know, definitely, even if it's not in the training data. Okay, so we need to reduce hallucination, and as a result, we're going to reduce our generalization. We're not going to generalize perfectly. We're going to be miscalibrated. Okay, so, and indeed, the post-training they do, which is, whatever, RLHF or some weird stuff, they do check their calibration after post-training, and it's not calibrated. It's not generalizing perfectly, which makes sense. And it reduces hallucination. So just want to give an example here of, do keyboards hallucinate? So you can go to your smartphone and you can say Adam Kalai died, and it will offer you some words, and you could, so I'm talking about generating from the language model temperature one. You could just click randomly and it'll work. And that's where I actually got this. And it'll come tell you I died in the cancer on April Fool's morning, and so on. Okay, so we don't tend to think of this as a hallucination. And why is that? Because, does anyone have a reason why, even if it used to be that they generate gibberish, but even if it generated grammatical stuff, it doesn't feel like a hallucination, right? And go ahead.
Well, okay, my take on hallucination is that when we use that term, colloquially, we're referring to language models misleading you, which is why it doesn't apply if the prompt was generate some fiction. They're misleading you about the actual state of belief.
Yeah.
In this case, it's just predict ahead, and so we don't think so.
Exactly. Even if it was a fact besides my name, whatever it's doing, if you said, you know, any Adam Clyde's birthday or whatever, like it'll get it wrong. And we don't feel like its job was to give facts. We thought it was trying to help us type, right? Right. It's just a predictive keyboard. And that's how language models are trained. The same way as a predictive phone keyboard, that's when they train that language model, it's the same way. It's trying to predict what you're saying next. Now you just repackage it. Exactly. I mean, at least the way it's, the way it's trained, the way it's pre-trained. Now we want it to work well. So just don't be surprised if the pre-training stage led, what's shocking is that the pre-training thing worked at all. It's just a keyboard, it's a darn keyboard that's just guessing what you're gonna type next. And the fact that that can be used to answer questions intelligently is kind of amazing. That's a surprise. Not that it hallucinates, well, that's what you would expect.
You also did a false premise.
Yes, but if I just said fact, Adam, Tom, and Kalai, maybe I said Adam, Tom, Kalai, in the next words, it'll just start generating gibberish. You know, it's not very factual. Because it's trying to guess what I'm going to type.
In practice, is there some understanding of like, as you increase the amount of training data, not new types of training data, but more of the same type of training data? And also if you make the model bigger, do you find that hallucination decreases?
I don't know. I mean, it's a good question. I'm sure that's studied. I mean, there's different aspects. So this is only one. The statistical aspect is like for certain distributions where you're just not going to cover all the facts. If it's a distribution which you can cover more and more of the facts, then this would argue that you would actually do better. But if it's a huge distribution where until you see, you know, a gazillion examples, you'll see, you know, you won't see repetitions, then this won't suggest that. But there's other aspects of things like for the book titles and the paper titles and stuff, it might be a computational, like a memory limitation that the model wasn't just dedicating it didn't have enough neurons to store titles and all the other facts it needed. So a bigger model might be necessary, but like that's not in our work, but it'd be really interesting to have a analysis of that.
You promised to say something controversial.
Okay, yeah, I'll get there. Maybe,
okay.
Yeah. Right.
Like the 3 Zs. If you do ask them, they all say Kazakhstan has 3 Zs in the name.
Which one? Which language model?
GPT-4o and Sonnet 3.5.
Really? I'll try that.
I understand there may be a gap between empirical and theoretical. So is it intuitive to say like if you train like with more epochs, they just reduce the hallucination? Because you saw these examples not just once, or multiple times. Because just increase the number of epochs. Right.
Yeah, say it again. You said?
So like you increase the number of epochs you
Yeah.
train.
It'll hallucinate less. Yes. Yes, it'll hallucinate. It'll just memorize the training data eventually. Maybe try cues. Like it's not great at counting letters. Maybe my example isn't good. It'd be interesting if you asked it how many Z's in Kazakhstan. Because I know the classic example, you ask it how many R's in strawberry, and it even sometimes gets that wrong. So thank you. I should use a better example. But any other questions? Okay, so got that. Okay, well, let me put my conclusions for this part now, and then if I have time, I'll say a couple other things. But okay, so I just want to mention that in the human brain, there's actually 2 language models. This is a little bit of a character, but it's roughly true that there's an area for listening called Wernicke's area near the ear for listening, and an area for speaking, which is closer to the mouth, called Broca's area. And they're 2 different language models roughly, and makes sense because you have to have one model which is good for listening and understanding, interpreting what you hear, right? Somebody says something, you have to be prepared to hear a bunch of things which you don't know to be true, right? They might be plausible. You have to be able to, you know, if you're doing speech recognition, you're trying to say, did they say Maya Shmaya died on? You have to parse things, so you need to have a good listening model. And it has to be able to hear a lot of unexpected things which you can't distinguish from true or false. Okay, and then, but you don't want to generate from this area, and there's actually called like a condition called Wernicke's aphasia, where people babble and basically hallucinate themselves. But instead, you know, you speak from the other area, And this process, all I'm saying about post-training for your question before, I'm not going into detail, but is this process is called post-training, where you essentially want to figure out how do we go from this predictive language model to a generative language model. And in some sense, the mystery or the miracle of language models was that it didn't take as much work as you might think. Like this predictive phone keyboard, which we all thought was just helpful as a keyboard, turned with a little bit of work, and you said, oh yeah, an expert, you prompted it by saying, oh yeah, here's what an expert said. And then you can use it to almost as a useful language model. Then you do need post-training. There's a lot of work, and it's an important thing. It's probably an underdeveloped area of language models. But it's a super interesting question, just like we saw in the birthday one, like what distribution do you want? That's the question of alignment and everything. And I think this is where we need all the cryptographers and people to come in, and the Alice Bob models to say, okay, what do we want here? It's no longer a statistical problem of just matching a distribution. It's really what's a useful model, what's an adversarial model, what do we want from these things? We want it to never be false, or what distribution do we want? And I don't think machine learning has a great answer for that, and that's called alignment. Any questions before I say a couple other things? So I just mentioned, I wasn't sure how long I'd have, so I prepared a couple extra slides. So one thing I wanted to talk about for generalization is instead of like a new thing that maybe we'll do instead of probably approximately correct learning is maybe you could call it probably approximately optimal learning, which is that instead of trying to match the best classifier in a family, I want to say you want to match the best architecture, best learning algorithm. So it's like too much, you have this neural network with 1 trillion parameters or something. It's too much to try to find the best neural network with 1 trillion parameters nowadays. It made sense when we were doing linear classifier. But with so many parameters, what's more reasonable is to find the best learning algorithm, the best transformer architecture, and so on. And so I don't have a lot to say on this, but like basically, you want to find a learning algorithm which works for given a family of learners, which is basically architectures, hyperparameters, it gets you expected error near the best in that family. Yeah, the learning algorithm outputs the classifier. So the classifier has 1 trillion parameters. The learning algorithm is the transformer code, which is like relatively small. So it's more realistic to try to compete with that than with the classifier. And it relates to a paper on generalization that I had a while ago with Vikas Garg, Katrina Liggett, and Stephen Wu. And like the setting we have is just, I'll skip over, but like the main setting is that you have many domains, and you're trying to learn across these domains, and you can find commonalities. Like you want to learn to generalize. You want to learn which features generalize, and which features don't, or which architectures and algorithms do. And so I won't talk about it, but well, in a prompt setting for language models to make it more relevant recently, you would say like, even you could just learn the best prompt. You could learn the best, let's think step by step. I don't know if you heard that, but that's like a trick you can add to any prompt, which makes it better. Often, not always, but often. Or you could try a bunch of other stuff. You could say, oh yeah, give me a prompt. I'll say, we'll try to solve it 3 times. We'll double check our work. There's any kinds of, and there's a lot of maxims that humans have, like look before you leap, or, back up your work, or things like that. And so, as the language models get smarter, we're going to want them to do that, right? To be safe, right? We're going to want them to learn in any setting where you take an irreversible action. If you can possibly back it up, you should probably do that if you can check with the user. So these high-level things we want to generalize, which go across domains. And so we want to learn these meta principles which go across many problems and out of distribution. But I say out of distribution is actually just that there's a distribution over distributions. And so what I have there as an example, let me skip over this, but so what is a distribution over distribution? So basically, if you wanted to train a self-driving car to do well, right? You don't just train it in one city. It could memorize the geography of that city and and even if you gave it 10 cities of data, it could just memorize it. What you want is find the algorithm which, when trained in 5 cities, does well in the other 5. If you found an algorithm which did well like that, then you would have confidence to release it on a bunch of new cities. Now, what if you don't have, your data is not nicely packaged and divided into cities or whatever. Like, what if you only had one city of training data? Well, what you could do is you could divide it north and south. Then sometimes you could find splits in your training data and turn it into a challenge of generalization across multiple data sets. Or, you know, the handwritten digits, you could divide your data weirdly into thin and thick things and try to find an algorithm which generalizes from one to the other. So anyway, okay, so I have those examples, but my conclusion is still that you know, I'm still very interested in what is it that we want from these language models. What I just gave you is one idea, and that's all I want to say. Thank you.
In the very beginning of your talk, you give a very good example, like miscalculation,
Right.
So after the talk, can you comment a little bit about that? Like, how can we differentiate these?
Yes, so that one is an example where you can learn. We could learn like a learning algorithm. It's not surprising to you that as a learning algorithm, we could learn to distinguish true multiplication facts from incorrect ones. Like a good algorithm could learn, you know, oh, 3 times 7 is 21. That's true. 3 times 8 is 19. That's false. And so assuming that we could learn to generalize that across some distribution, we don't need to hallucinate. So I don't think language models information theoretically need to hallucinate on arithmetic problems. And they might even learn to generalize out of distribution there, right? Like they might learn the fundamental, because there's a succinct classifier that they've learned, which generalizes.
So I mean, that miscalculation happens because it doesn't learn that way.
Yeah, it's a lower bound. So maybe sometimes the language models don't do well. That's just a failure of theirs to do a good job in learning the underlying principle.
Okay. Do I understand like generative language model, like the distribution we want to, you know, spit, will be different than the like distribution we are learning. So it's kind of like a conditioned version of the input distribution. In that sense, like we define the generalization based on the, you know, like unconditioned version of the like domain distribution.
Yeah.
In that sense, like, do you think we are miscalibrating value, you know, in the fine tuning? Because if we were to define the generalization with the conditioned version of actually we're calibrating our language to, you know, like follow our preferences.
Well, I'm not sure I totally understood. I mean, there's prompts. Are you getting at the issue that you give it a prompt which might be out of distribution or very different from the training distribution? Or not really?
No, like what I was saying is that like our preference is a little bit different than what we see, like our.
Oh yeah. And same thing with humans, right? We hear kids talking, or we hear a lot of swearing, or whatever. We don't assume that like somebody who grew up in an environment where there's a lot of swearing, they themselves will swear. You hear that, but you do this process, like similar to post-training, where you then learn, okay, well, that's what they said. I'm not going to do that because I have a different preference.
Let me ask this question: like, if we define the generalization with the, you know, like the distribution we preferred, do we have this kind of lower bound there too, like for?
I don't know, but I mean, we don't even have access to that ideal distribution. I don't think, do we?
Yeah, I think that's fair.
That's a good question.
So based on your lower bound, could you output for any question that is given to ChatGPT what like the lower bound that it hallucinates?
You could try to like do some computations on different domains to figure out what you'd expect the rare fact rate, right, in certain domains, and give a lower and see if their lower bounds make sense. If you do an experiment, that's a good idea. I don't want to keep people from lunch, but yeah.
General prompt transform. Is it there are people who play with ChatGPT a lot? And they know how to do that. And I don't know most of the time. So the question is, but it's
right.
An art, or maybe more than an art. What isn't it something that the large language models should offer you?
Yeah, they do. I mean, people. Sorry, like OpenAI doesn't, but researchers write programs that search over prompts and then evaluate them and try to find the best prompt. Also, people do it a lot to jailbreak the language models and get them to misbehave, and they write programs to search over those things. But yeah.
It could be a front end of the language model itself.
Yeah. Yeah. I mean, when you ask, sometimes when you ask for like an image or something behind the scenes, it might transform your request to another thing, which it then uses. Thank you.
I'm still thinking, like giving more thinking about my first question. So, because I still hard, in my opinion, it's still hard to differentiate. Like I give you an example. So, assuming our training data set, it only considers 2 digits multiplication, which is uniform.
Right.
So in your theory, it's actually hallucination instead of miscalculation, because
if it gets it wrong, yeah. Wait, why would it only appear once?
I mean,
if you have 2-digit multiplication, there's only like 10,000 of them. You'll see them many times.
You will see some like random calculation results on the internet, like 4 digits multiplication. Like this happens a lot.
Yeah, so that's the second result about learnability, not about how often things appear. Because in my first version, everything was independent, and one fact is true is independent. But in the second one, it was a question of learnability. Can you learn from the true facts the general principle which distinguishes a fact from another one? And I claim for multiplication, you can in principle learn the underlying thing which distinguishes a true multiplication fact from a false one. I know I'm keeping people from their lunch break, so I'm happy to take questions. Thanks.
Everybody's here.